And recording has started. And so welcome to Tuesday. You guys having a good Tuesday so far? All right. About to get even better. So this start page here looks a lot like yesterday, right? So I've got all the topics I want to cover this week. We're gonna get to probably do this much today, right? And then save some of these for a couple days, right? So it's on schedule. Right. You guys remember that this page that I did a couple with you guys yesterday is going to be your guys' first homework. I'll pick this up on Friday. And your guys' quiz on Friday is also going to look really similar to this. Okay. Also on the quiz on Friday, let you guys know now, I want you guys to be able to take a problem like this one and break this weight vector into components. That's exactly the question. This looks a lot like your starter question yesterday, except I made one change. I changed this angle from 30 degrees to 37 degrees. So let's solve that question. Okay, read this real fast. Got this block weighs 100 newtons, just like yesterday. It's on this incline 37 degrees, so this new angle. Okay. So this question's the same as yesterday. This block is partly pushing into the incline. It's partly trying to slide along the incline. Let me flash up one of the pages from yesterday's notes. Here it is. You guys remember we were playing around with the angle in our minds? So this angle at one extreme could be 0 degrees to the horizontal, and at the other extreme it could be like a wall, right? And as you transition from left to right, make the incline steeper, steeper, steeper. Remember that, well, for a flat surface, horizontal surface, all of the block's weight is being pushed into the surface. But that's less and less true the more vertical it gets. Right? It tends to want to slide more and more parallel to the surface. Okay. And what you guys had to do, I'll show you guys some more notes from yesterday. You guys had to understand SOHCAHTOA, some basic trigonometry, and I rearranged these sine cosine definitions in terms of how we usually use them in physics almost all the time. It's good short cut to know right here. Opposite is hypotenuse times sine theta. Adjacent leg is hypotenuse times cosine theta. There's also a way to extract an angle if you only know sides, right? Using an inverse trig, in this case inverse tan. And we're looking at, I'm thinking about these four. If you take those middle two frames, we sketched those up and we did took those vectors and broke them into components. Right? So kind of a shallow angle, kind of a steep angle. Right? Remember these components. Right? And you guys remember too that these components are perpendicular and parallel to the surface, because that was the question is, what's this block do? How is it interacting with the surface? Okay. Okay, you guys remember that? So that's a quick crash course from yesterday. Right, so back to this question, 37-degree angle. How much is the block sliding? How much is it being pushed actually into the surface, and how much is it trying to slide along the surface? Okay. So who knows the answers to either of those questions? Who's got it by now? Give you guys a few more seconds. You know somebody's going to get this. Katie?
Is it 60.2 and 80?
About 60 and 80 newtons. Yeah, and then you just saying the same thing? Yeah, about 60 and 80 newtons. Yeah. All right. Right, so they got it. You guys are probably in good shape for quiz on Friday when I ask you guys this question. So sketch this out nice and big. Okay, got my incline, got a 37-degree angle. I've got a block with a center of gravity. Okay, so it's going to start us off. Okay. Oh, and this block has a weight. Weight pulls straight down. 100 newtons. Okay. Of course, weight's a vector because gravity's the Earth is pulling a direction. This case down. Okay. And then since everything is relative to the surface, I need to introduce a new coordinate system. You guys remember that's parallel perpendicular to the surface? Right? So break out the pink ink, do an axis that's parallel to the surface, that one right there. And then perpendicular to the surface, black, something like that. So I've got a new coordinate system that's oriented according to how it's going to help me answer the question. I'm going to break out this green ink and break this 100 newtons into components. Okay? So this 100 newtons is going to effectively become the hypotenuse of a triangle. Okay? And that's usually how this class works. Usually, whatever vector you have that you're about to break into components, well, it's going to become the hypotenuse of a right triangle. Okay? So that 100 newtons, you know what can help too? I don't know. This is something I did not show you guys yesterday, but if you rotate the entire paper, and now you're looking at those pink axes, see how this vector looks kind of down to the left relative to those axes? Now, still, gravity's still pulling down, right? But it just turned the whole world, right? You guys see how, from this point of view, this axis is, this vector is partly pushing like along this axis, and then partly along this axis like this, like that. Right? And notice the two components are always at what angle compared to each other? 90 degrees, right? You guys see like a 90-degree angle here? That's always going to be true. Okay? And that short component that I just drew, does that look parallel to the surface? It sure does, doesn't it? You guys see that? Let me rotate the world back to how it belongs. Gravity restored. But see how that is parallel to, it's not parallel to the ground. It's parallel to the surface. Okay, you guys see that? Okay. So by Friday, you guys will be able to draw parallel lines? You guys will be able to do this by Friday, right? Okay. What is this angle right here? 37 degrees. It kind of looks like it, right? It kind of looks like the same, right? And it always is. If you want to do a full geometry proof, then figure that out. Right, and then, okay, now think about the rearranged version of SOHCAHTOA that I gave you guys yesterday. I boxed it in the notes. Right? This component is equal to what times what? What times what? Start out with your 100 newtons, which is like the hypotenuse of this triangle. You guys see a nice little right triangle down here, don't you? Right? Yes, times sine of 37 degrees. Yeah. And if that's true, then do you think that this component is, 100 newtons times cosine of 37 degrees? There you go.
Are you gonna put that, you're gonna want us to put the units on it?
Oh yeah, always include your units, right? Yeah, that is really important for a physics class. Yeah, there are very few quantities that don't have units. I mean, I'll give you guys an example, one that doesn't. It could be like coefficient of friction. It's like newtons per newton, it cancels out. So there are a very small number of instances where you could have a number that doesn't have a unit attached to it. But yeah, otherwise you have to have some context. Like 100 what? 100 gallons, 100 pounds, 100 newtons, right? So yeah, good call. So 100 times sine of 37 degrees is, it's like almost exactly 60 newtons. I'll just call it 60 newtons. And if I replace the sine with a cosine to do this one, I've got 79.86, blah, blah, blah. Okay. Oh, it's very, very, very close to 80 newtons. So I'll just call it like 80 newtons. Okay. And, guys, do you see a special triangle up there? Special right triangle. What special right triangle is that? 3, 4, 5? Yeah, Shane saying 3, 4, 5? Who else said 3, 4, 5? Oh, yeah, I think Maren got it. I bet a few guys out there were looking saying, that's a 3, 4, 5 right triangle. Right? Because 60, 80, 100, doesn't that reduce to like a 3 to 4 to 5 ratio? Sure does, doesn't it? Divide by 10, you get 6, 8, 10. Divide by 2, you get 3, 4, 5. Right? It's a 3, 4, 5 triangle scaled up by a factor of 20. Right? Or, I bet so many guys in there were even looking at 37 degrees saying, I know why you picked 37 degrees, because that angle always corresponds to 3, 4, 5 right triangle. Right? You guys probably saw that ahead of time. Okay, guys get it? Right, so that's the answer to that question. Let's see what I got for you guys. What's next here? There we go. All right, so break out that page that you guys have had since last week. You guys remember this page? Well, this side I did a couple of these with yesterday. Remember, this is your guys' homework, and it's going to take up on Friday. There's going to be quiz questions that are very similar to that. But let's do the other side. So this side, there's 5 triangles and a table. Okay. All right, and we'll do probably not this whole thing, but we'll do at least a couple of triangles. Okay, so you guys do see that these are all right triangles, right? Okay. No, we all have slightly different paper. So, for example, I have a coupler triangle. You may or may not have a coupler triangle, but you have a bunch of triangles. Okay. How about this table up here? Okay, so this table has 5 rows. Hey, and each row has one of the triangle names on it. Okay, so each row corresponds to one triangle. How about the columns? What's going on with the columns? Okay. Well, if you look at hovering above the columns, it says I want you to either measure, make some measurement, or calculate something. So measure, calculate. Okay. The measurement is where the science part of this comes in. So all those nice notes I gave you guys yesterday about SOHCAHTOA and rearranging and blah, 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 that's very strict math point of view, but science is all about like observation, measurement. Okay. So we're going to see how this compares to math theory. Okay. So I want you guys to measure, and I'll just with you guys for a couple of days, alpha and beta, so the 2 acute angles. Okay. There's also a 90-degree angle that's implied. I didn't put it in the table, but you guys know these are all right triangles. Okay. And then I want you to measure the 3 sides. So measure side C, measure side A, and then skip a few columns. This will make sense in a few minutes why that I took the last measurement way the heck over here. Measure side B. So let's go and do that. I'll take this coupler triangle. If you have coupler, you can, well, oh, do I have, wow, I just realized man. Yeah, I didn't realize until just now. I copy pasted this table to all the different versions. Okay, oops, my mistake. Okay, well, you can change the names of the triangles to just the ones that you have. Okay, you guys get that? So, that was a transcribing error. I was gonna do a new and improved version of this. So I'm gonna cross out Curry because I don't have a Curry triangle, but I do have a Kepler triangle. Okay. So first I gotta measure the angles in degrees. I know probably most of you guys use a protractor, but I always have a few students who haven't or haven't for many years. So give you guys a crash course on protractor. Protractor measures the size of wedges, right? Like an angle. So I need like, 2 sides that are gonna, 2 legs that are gonna intersect, and need to somehow figure out how many degrees that is on the protractor. Okay? So I'm gonna take this node of the protractor. I'm gonna park it right on this corner, right there. Okay. I'm gonna zero out the bottom leg. Okay, so rotate the whole protractor. Zeroes out right there. Okay. And then the other leg, in this case the hypotenuse triangle, will naturally cross through the number of degrees it is. Okay. Well, it's crossing through 2 numbers. Looks like it's crossing through like 22 and also 158. 22 and 158. Okay, so what is alpha actually equal to? 22. Okay. 158 would be this giant angle over here. Oh, alpha and beta, I guess it has to be less than 90 degrees. I mean, there are acute angles. Okay. So 22, so I'm going to go to alpha and write in 22. Okay. Now, if you wanted to, you could have measured from the other point of view. So what if I rotate this whole paper upside down? Okay. Remember, there are 2 sets of numbers on the protractor. The inside numbers, at least on my protractor, are measuring counterclockwise, and the outside ones are measuring clockwise. So if I turn this whole paper upside down, it tries from their other point of view, we use the same method. But this time I'm going to zero out the hypotenuse, okay? And the other leg naturally crosses through, 22 degrees. Okay, so it all checks out. Okay. Yep.
So when I flip my page upside down, I get 40 exactly, but when I do the other side, I don't get like a number that would add up.
Let's go back.
I mean, it's 40, sorry.
I guess you did.
And then here,
I got the same triangle.
around.
One section, the string.
So I wouldn't.
How do you do okay, yeah, so I'll keep going over this. Yeah, you guys can just follow along with me. I'll do a couple of triangles, and then by then, you guys should have a good idea. Okay. Yeah, I do have to get the other angle beta. Now, some of these triangles have kind of short sides, and it's kind of hard to measure with the protractor because the sides are real short. I'll show you guys how to take care of that. Okay. So let's say I'm trying to measure this angle beta for Kepler. Okay. One way I could do it is to park this node right on this corner, zero out the short leg, and then the long side, which is hypotenuse, is going to cross through. See, that looks like 68 degrees. 68. Okay. But what if you did it from the other point of view? I think this was probably your actual question. What if you had Kepler like this? You zero out the long side, everything's good. You say, what's the size of beta? And oh boy, that's real short. That's nowhere even near the numbers, right? I would need it to extend way out here. I'd need like a blown up version of this triangle. The way you can handle that is you can just extend this leg. So use the straight edge right here, straight edge, okay, and just extend the side, just like that. Put on an extension, and then now I already have a value for beta. It should be 68 degrees, so it should still be 68 degrees, but you just double check them. So zero out. Okay, so node parked on the corner. This side zeroed out. This goes through. Yep, something like 68 degrees. Okay. Is that right? Okay, so I got a couple of angles. Now, what did my two angles add up to? They do add up to 90. Now, when I did this last class, show you guys a little bit different example. I had a Maxwell triangle, and my two angles added up to, what do those add up to? 22 plus 69 adds up to 91. Ooh, okay. So if they add up to 91 degrees, should you cross out one of those numbers and change it so they do add up to 90, force them to add up to 90? What do you guys think? Or should you just leave it so they add up to, is anywhere between 87 and 93 okay? Okay. Well, it depends what class you're in. So if you were in a math class, the philosophy would be those triangles, those angles better add up to 90. You go back and erase things and measure, make sure they work. Okay. But because this is a science class, a little bit different philosophy, you really care about your observations and measurements. Right? That rules over any theory that's out there, right? The hard data takes precedence. I guess if you wanted to go back and remeasure these and then make an adjustment based on those remeasurements, that might be okay. But I would accept those. So as long as they add up anywhere between 87 and 93, that's usually right. Now if they add up to like 77, then it's like, okay, something's like way messed up, so you gotta go check that. Yeah, Reagan? Okay, yeah, that's a great question. That's right in line with the same idea. That's adjacent to what we're talking about too. Because if you know one of the angles, could you just do 90 minus that and get the other angle? Okay. Well, if you were in a math class, yes, but a science class, no. Right? Because yeah, this class, it's important that you have the actual measurements, right? And it says measure, there's an assumption that there's an implication there that you measure that, and that's an actual measurement you got. Now, in the back of your mind, you should really add up to 90 degrees, so as long as they're pretty close, then you're going to be all right. Okay. Next measurement. So we're done with the protractor for a while. Break out the ruler and get what is the side C in centimeters. So this is looking like, is that 8.1, I think? Okay, so I think that's 8.1 centimeters for Kepler. Okay. The side A has a length of, let's say 3.1, 3.1. Okay. Then I need the side B, and the side B is, mine looks like 7.5, I'm going to call it. Okay. Now, this one, you have to skip a few columns to get the last measurement. You'll see why in a few minutes. That's 7.5. Okay. So now I've got my 5 measurements, and of course the right angle is implied. Okay, so I got 2 angles and 3 sides. Okay, so the 2 acute angles and 3 sides. All right, now the rest of this row, I want you to do some calculations. So we're going to break out the calculator, do some calculations. See what we're supposed to calculate. First one says C times sine of alpha. Hey, you know what? C times sine of alpha, that looks a lot like those notes I gave you guys yesterday. You guys remember, I keep showing you this, but it's because it's so important. You guys remember this box in right here? C times sine of theta, C times sine of alpha, right? That looks like, shouldn't that tell you something about the opposite side? Right? Opposite of the reference angle, right? Whenever you're dealing with sine, right? Calculator, C times sine alpha, if I do 8.1 times sine of, now be careful also, alpha and A are two different values with two different units, so completely different ideas. So type in 22 for 22 degrees, okay? Now before I hit enter, take a look at the geometry of this triangle. If I start with hypotenuse C and then multiply by sine of alpha, isn't that going to flip it over to the opposite side, which would be like this leg called A? Wouldn't that be true? Okay. And I have a direct measurement for A. I know it should be 3.1 centimeters because that was my direct measurement, right? So I hope, if all this math theory is right, that when I hit enter, this is going to say something very close to 3.1, right? You guys get that? Let's see. Oh, 3.03, blah, 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 blah. Okay, so that rounds to 3.0. Now, if I only have two sig figs to work with, then I guess that's as much as I can ever really know, right? But that's very close to my measured value. I'm happy with that. Right? Not exactly, but really, really close. Okay. Next column, C times cosine of beta. If I again start with hypotenuse, and then I bounce off the angle beta, but I'm using the cosine. That would be the leg that's adjacent to the angle beta, which is also the side A, isn't it? Right? Huh. So we're getting different perspectives of how to get the side A. The direct measurement, the sine of alpha, now the cosine of beta. So cosine 68. Okay. And I'm getting, again, 3.0. Okay. One thing you'll notice if you do enough of these triangles is that anytime your alpha beta add up to exactly 90 degrees, which in this case they happen to, okay, that the sine and cosine perspectives on any legs will be exactly the same number, right? Down to like 100 digits in. Right? It's not so crazy. Exactly. Yeah. Okay. Okay. And then you know what? If you kind of stand back and look at the table as a whole, how many guys happen to notice that there's a dark rectangle around these four columns? You notice that there's a dark rectangle. How many guys see it right now? See this dark rectangle? You guys all see that, right? Right? Huh. Do you think that maybe, bet you guys can put two and two together, do you think that maybe the four cells in each row refer to the same side? That's probably what I'm getting at, right? It's probably why I boxed them in. And there's like the same number over and over, pretty closely. Right? So this last one says the square root of c squared minus b squared. Hey, that's the what in disguise? That's the Pythagorean theorem. You guys see that's the Pythagorean theorem in disguise? Right? Just in case you didn't catch that, I just wrote, you guys, I'm going to do an algebra review with you guys tomorrow too, but you guys remember how a squared plus b squared equals c squared? That is the Pythagorean theorem, right? But what if you wanted to solve for one of the legs and you knew the other leg and the hypotenuse, right? Could you do some algebra and get that? So you guys have three algebra terms, right? A squared, b squared, c squared. Right? I need to isolate that a. So first step, I'm going to take the b squared, subtract it over. And then I'm going to do what's both sides? Square root. Right? I want to undo that square by taking square root. As long as I do it to both sides, it's all good. So square root of c squared minus b squared. The difference? Right? Oh, that's exactly what that says right there. Right? Same thing. Right? So that's where that came from. Okay, guys, we're on to that. Right. So square root of 8.1 squared minus, remember b is way the heck over here, so don't forget that, 7.5 squared. I'm looking at 3.059, blah, 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 blah. That rounds to 3.1. I have two sig figs to work with. Right. Kind of somewhere between the sine cosine versions and the direct measurement. It's all right in there. It's all in the ballpark. Right. Right, finish this off. I bet you guys probably pick up the pattern of how this whole table works by now, right? So I bet these last three cells probably refer to the side B. I hope they're all pretty close to 7.5 centimeters. from different points of view. Let's see, c times sine of beta, c times sine of beta. Yep, that would definitely refer to side B. So I'm going to go 8.1 centimeters times sine of 68 degrees. That is 7.510189. Okay, so 7.5. C times cosine of alpha. Yep, that also refers to the side B. So pop in a cosine, 22 degrees for alpha. That's also 7.51, something. And then the square root of c squared minus a squared. Well, you guys figure out that's the reverse Pythagorean theorem. Okay. Do you guys remember the power technique I showed you for square root yesterday? Did I tell you guys how to take a square root with the power? Oh, maybe I didn't. Oh, I did? It's a power of what? 1/2. Yeah. I'll do that because sometimes that's actually a really fast way to take square root. So I'll just start with an open parenthesis. Let's do 8.1 squared minus 3.1 squared. Okay. I've got that all grouped together. Okay. Notice there's no square roots yet, just the difference of two squares. Then hit caret and 0.5, and it's telling me, oh, 7.4833. That rounds to 7.5. Okay. Oh, actually, that is good because it's like the same number. It looks like. Usually, if there's one, like if you do a bunch of triangles with this page, if there's one method that tends to be an outlier and give you kind of like, oh, that seems kind of far off. Let me double check. No, it's definitely far off. It's usually the Pythagorean theorem version. Like I wouldn't be surprised if that came at like 7.1 or 7.9. Like, okay, but in this case, it all looks good. That's right. All right, let's pick another triangle. I'm gonna pick this Tesla triangle because it looks fun. It's all tall and skinny looking. Let me scratch out this guy because I don't have that one. Right in Tesla. Okay. All right, so we need alpha and beta. So I'm going to zero out. You know what? I'm going to use that technique I showed you guys. One of these legs is real short. So let's pretend I'm taking it. Actually, I will take this clockwise. So I'm going to extend this leg. Ooh, I think I got a question on Google Meet. Where is this? Okay, yeah. So the question online is, if you don't have the same triangles that I have, yep, everybody has different triangles. Now, I just noticed at the beginning of this class that I had copy pasted the same table for everybody. So you can cross out some of the names on the table and just write in the triangles that you have. Yeah, we all have different triangles. Okay? So if you don't have a Tesla triangle, that's okay. Just pick one of your own triangles. Okay? So I extended that short leg. Right. Let's see, I'm going to zero out this corner. Park the node on the corner, zero out the hypotenuse, and my extended leg goes through, that looks like 69 degrees right there. So go Tesla alpha, it's going to be 69 degrees. Okay. And what is Tesla beta? That is 21 degrees, 21 degrees. Now, I'll do a quick check. Alpha plus beta, 69 plus 21. It does add up to 90. Okay. Again, if it was pretty close to 90, then that'd be all right. That's good so far. Okay. What is the side C? Let's see. So this is 7.3, I think I'll call it. I'll call it 7.3 centimeters. Okay. Side A. If you have your own Tesla triangle and you're like a millimeter different than mine in the measurements, then that's all right. It looks like 6.8, I'm going to call it. 6.8. Okay. And then the side B, the real short one, looks like 2.6. That's way over here, 2.6. Okay, so I've got my 5 measurements. Now, calculator time. Okay, so first calculation, c times sine alpha. So if I do c times sine of alpha, that should refer to the opposite side alpha, which is side A. So 7.3 centimeters times sine of 69 degrees is 6.84 1, 5, blah, blah, blah. Okay. Yep, that's the same as I measured it. C times cosine of beta, beta is 21 degrees, is also 6.81, blah, 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 blah. Okay. And then square root of c squared minus b squared. So it's 7.3 squared minus 2.6 squared. That is, oh, hey, that's also 6.8. 6.82, blah, blah, blah. I was kind of secretly hoping for a counter example I'm hoping that one of these Pythagorean theorems is going to be off a little bit because it usually is, but I guess not today, given us like the exact good numbers. Before I finish off this row, is anybody on their calculator getting negative numbers? Is anybody getting negative numbers on the calculator? Right. If you are, usually what's going on is that your calculator is in measuring radians instead of degrees. Remember, there's different ways to measure angles. Okay, so we're all using degrees today. Is anybody running into any other trouble? You guys all right? All right, so finish off this row. C times sine of beta. Now, C times sine of beta should refer to the opposite side, which should be this little tiny short leg B. I hope it is. Let's find out. So 7.3 sine of 21 degrees is 2.616. Looks like 2.6 something. Oh, that's just the same as I measured it. C times cosine of alpha, alpha 69 degrees, is 2.61, blah, blah, blah. Okay. And then finally, reverse Pythagorean theorem, got square root of c squared, 7.3 squared, minus a squared, 6.8 squared. Let's see what this is. 2.655 something something. That rounds to, well, that does round to 2.7 to 26 figs. So, let's do that. How you guys doing out there? Who's got questions? All right, so here's what we do is you guys are going to eventually turn this page in on Friday, right? You guys know because you've got homework on the other side. Right. When you do, as long as you have at least 2 rows, just like I have here, then I'll give you full credit. Now, if you want some extra practice, then you've got lots of extra triangles. Okay, but as long as you have at least 2, okay? You guys good? You guys ready to move on? Next time? Okay. So, real fast, just for fun, can you guys think of an example of a triangle where the angles would not add up to 180? And there is actually a correct answer to this. Does anybody know when a triangle, the angles do not add up to 180? Yeah, you can say.
You mentioned earlier non-Euclidean.
What?
Non-Euclidean.
Oh, non-Euclidean. I think that's the fancy term for what I was talking about. Yeah, so you're saying like if it's maybe like on a curved surface? Yeah, Alex got it. All right. Nobody got it last class. Wasn't sure if you guys were, but yeah, Alex totally got it. Okay. I'll draw an example for you guys. You guys see this planet Earth right here? That could be planet Earth, right? Okay. Let's say we're walking around on Earth. So we're going to start up here with Santa and the elves and hang out at the workshop, and it's all cool. Right? Then we walk down south, straight south to the equator. Okay. Make a 90-degree turn, start walking along the equator. Right. And then after similar distance, make another 90-degree turn and walk back to the North Pole. Right. Then make another 90-degree turn, and then just keep doing that over and over and over again. 3 90-degree corners. That adds up to 270 degrees, doesn't it? That's more than 180. Okay. But that's not a flat triangle. It's like has curvy sides. Okay. But the 180-degree rule works as long as it's a flat triangle. Okay, so that's fun. Okay. Let's look at do a little bit of tip to tail vector additions. Okay. So there was a question I threw at you guys a while back that had to do with the plane. We're going to see what else we can do with these vectors. Okay. You guys know about vectors, components. Okay. And there was a question that I threw at you guys that had to do with a plane that's like flying in wind. You guys remember that? Okay. So let's say this plane, by itself, its engines can power it at like 80 meters per second, something like that, right, relative to the air around it. Meters per second, is that kind of like miles per hour, some kind of distance per time? Miles per hour, meters per second. We get used to this in this class because we're going to be using metric system to see that all the time. Okay. That's how fast a plane can fly. Okay. What if this plane is now in a wind that's also blowing north. The plane's pointing north, going north, and the wind is also blowing north at like 60 meters per second. Okay. How fast is that plane going relative to the ground? You guys would say, what's 80 plus 60? 140, right? So somebody on the ground has a radar gun. They're pointing up at the plane. Doesn't the plane fly past them at 140 meters per second, right? Because 80, this is really the plane relative to the air. The 60 meters per second could be the air relative to the ground. If you add those two together, you get 140. Okay. How about this? What if the plane is fighting the wind? The wind's blowing back against the plane at 60 meters per second, right? 20, right? It's going real slow relative to the ground. So 80 this way, 60 this way. It would leave you with a very short resultant, right? But what I want to draw for you guys is a question I threw out there but never answered. What if this plane is now in a crosswind? Same magnitude of the wind, it's going 60 meters per second, but now this wind's going straight east. Notice I've connected these vectors. This is the term I've been using, but I'll put it in writing now. Tip to tail, say, vector connection. Tip to tail, okay. Because the plane is always pointing north, going north. The wind is always blowing east. So how do I connect these vectors? Well, I connected the tail of one vector to the tip of the other. Okay. And that's going to give me a resultant. Okay. So if I go from the tail of the first guy, which is here, to the tip of the last guy, which is right here, you guys see I'm going to get, so this is called the resultant, right there. Okay. You guys think that that's the direction that the plane actually flies relative to the ground? Yeah, because it's trying to go north. It's always pointed north. Its nose is always pointed exactly north, just like the picture. Right? But it doesn't actually move exactly north. It moves kind of northeastish. Right? Okay. And also, you can figure out its total speed if you know. Well, let's put together what we've been talking about last couple of days. So some guy is down on the ground, points a radar gun up at that plane. What does that radar gun read? And you guys say, what's the magnitude of that green resultant? 100. Oh, Shane said 100. Well, said 100. All right, and then Tristan said 100. Yeah, 100 meters per second. How'd you guys realize it was 100 meters per second? Okay, yeah, I'm hearing two right answers. Pythagorean theorem, 60 squared plus 80 squared, take the square root, you would get this number. Some of you guys recognize that this is actually a 3, 4, 5 right triangle, right? Length ratio 3 to 4, gotta be 5. Scale it by factor of 20. Yeah. So relative to the ground, this plane's going 100 meters per second, but it's going northeastish. Hey, how much northeast? What is this angle right here? Yeah, 36.7 degrees, probably rounds to about 37 degrees, right? And in general, how do you get it again? Yeah. Is that Nita saying? Nita? Nita's saying inverse tan of opposite over adjacent. So 60 meters per second over 80 meters per second. Now, of course, the units cancel out, but good practice time. Yeah, that'll give you about 37 degrees. This is flying 37 degrees east of north. Okay. Good point. Right. Yes, sir? Right. Okay. Let's do another example you can do with vectors. What if I've got an object sitting in the middle of the room and lots of friends playing tug of war on this object. So we've got one guy pulling, maybe this looks like a baseball, right? Maybe one guy pulling up and to the right with 100 newtons of force. Okay. I've got one of his friends pulling, let's say his two friends are counteracting him, but they're both kind of weak. Right? This guy's kind of weak. This guy's kind of weak. Okay. This guy's pulling with, like 20 newtons of force, and this guy's pulling with like 30 newtons of force. going the opposite way. Overall, which way is that baseball gonna move? Yeah, it looks like this guy's so strong, it's still gonna move up and to the right. Okay, maybe not with a full 100 newtons of force, probably a little bit less, because these are gonna make sense of this. Well, I need to introduce a Cartesian plane so that we can break these into vectors, and then we can make sense of the vectors. Okay, so there's a Cartesian plane. Okay, how much to the right or left? How much up or down? Okay. And this 100 newtons, do you think I could break this into components that look kind of like that? Right? Okay. And then same thing with these other guys. Now, whether you want to put the triangle on top or bottom, it's up to you. I probably drew these a little too small, but I think I'll be able to. Actually, this is going to be okay. And I've got one triangle kind of on the bottom-ish, one kind of on the top-ish. But it turns out it doesn't matter which way you orient the triangles. Right? As long as you get the horizontal and the vertical components of what's going on. Okay? You guys see that? Okay. Now, I'm going to shortcut this a little bit because you guys know if I gave you this angle, you could do 100 newtons times sine of the angle is this vertical component, 100 newtons times cosine of the angle is this component. Okay, you guys know that, right? I'm going to make up some numbers though. Let's say that this is it will go 80 newtons here, 60 newtons here. Just make that a 3, 4, 5. Just okay, so that's easy. Okay. There's 30 squared minus 20 squared. Okay. Let's say this is a 10 newtons straight down. This is about 28 newtons to the left. And then about 20. This is about 10 newtons to the left, and this is about 17 newtons down. Okay. Let's ignore the original vectors and just focus on the components. Okay. You guys could get to that point, right? If I gave you the original 3 force vectors and the angles that they were at, you guys could figure out all 6 components, right? 1, 2, 3, 4, 5, 6. I'll go ahead and circle those components. Boom, 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 boom. Okay. Can you guys figure out where this problem would go from here? That this ball is being pulled overall, see 60 newtons to the right, take away 28 to the left, take away 10 to the left. You see that? Okay. So I might say this. I say the net force in the x direction is 60 minus 28 minus 10 newtons. Those are all newtons. Okay. But 60 minus 28 minus 10. That's 22 newtons to the right. Right? Overall, it's still being pulled to the right. Okay. The right still. And then the sum of the forces in the y direction would be, looks like 80 newtons minus 10 newtons minus 17 newtons. Right? But it's 80 minus 10 minus 17. That is 53 newtons up. Okay? Got that? Okay. So you could, okay. So then last thing I could do is I could put those components back together. I could say that overall this ball is going 22 newtons to the right, 53 newtons up. So it's going to look something kind of like this. 22 newtons to the right, 53 newtons up. And so the overall effect is going to be a little bit to the right and then a good deal up. So you pull up something like that. Right? You guys that? Put everything back together at the end. Okay. Right. Now, last thing I want to show you before you take off today is I showed you the method to get to the final answer. Just a couple steps away, Pythagorean theorem, inverse tan, all that stuff, figure out. Using the component vector method, you could use the tip-to-tail method that we were just using for the plane. Remember, the plane I used a graphical method to add vectors together, right? But I could bring in a third vector, like here, or a fourth vector, or a 10th vector. I'll switch my screen over. I want to show you guys It's a small piece of an animation. Use this for a moment. So remember all the stuff I'm talking about. There's textbooks about this. There's YouTube videos. We got a type of YouTube video out there. So, if you guys see go back here. Okay, so see all these crazy vectors, right? See how maybe you're following a path through the forest, right? You have to follow that blue path, then the red path, and the green path, and the yellow path. So that overall, if you started down the bottom left, you end up at the tip of that purple vector. You guys see that purple vector is the resultant, right? Of all the vectors have, could I add them together in any order that I want? Right? Watch this. All those vectors got to slide around, but they don't change orientation. Watch this. See how none of them rotated? Now we're going yellow, followed by green, followed by blue, followed by red, but we still end up with the exact same purple resultant. Okay? Let's see, one more time. Now it's green, followed by red, followed by blue, followed by yellow. None of them rotated, but we just added them together in different order. We always got the same resultant. Okay, guys, yeah? All right. So tomorrow we'll hit some of these other topics. Yeah, continue this adventure. You guys have a good Tuesday. I'll see you Wednesday. See you guys.